Okay, can you hear me? Because I can't see anything in the discussion area. If you can hear me, just type anything in WeChat group, okay? Can you see the slides and hear my voice? If you do so, please type something in the WeChat group. Okay, so finally, I can see the contents from the discussion areas. Good. But there are only 3 students in the class. Okay. Okay, let's begin. In last class, we just learned something about the history of the operating systems and the hardware of the computer. In the end of the last class, we just talked about this important concept called interrupt. We know that in the modern operating systems, more than one programs can run in the same computer, right? It means you have to deal with a lot of issues caused by multi-programming. Among those technologies, interrupt is very important to deal with the switch between different
processes or among different programs. So we have to understand this important concept. The interrupt is just a signal. Okay, hold on. The interrupt is just a signal sent to the processor. So who is gonna send an interrupt to the processor? I mean, send to the CPU. It can be emitted by this signal can be emitted by any hardware resource or even some software. It means when some code runs in is executed and it will have some error or something like that, then the interrupt just emerges and sent to the processor. So when the interrupt happens, it means some event had to be dealt with by the CPU. For the CPU, it has the right to deal with the interrupt immediately, or it can just enable, it can just disable all the interrupts, because sometimes maybe CPU is handling some processes very important with higher priority, or maybe even CPU is executing some codes from the procedure or handler used to handle another interrupt. So it's possible that when the interrupt is sent and then nothing happened to this interrupt, because we have an interrupt controller to decide which interrupt can be processed by the CPU first. They have a list and they have their own rules to decide among if there are some interrupts at the same moment, then we all during a period some interrupts happened, and they are just they're just listed in the table, and the interrupt controller can decide the next interrupt to be dealt with according to certain rules. So why the interrupt is important? Why we say we say that interrupt is very important for the multi-programming, because we have to switch the programs one after another, because all the programs in the memory, they just take turns to use the CPU. Sometimes if there are no interaction between the computer and the users, they just follow the schedule of the operating system. Operating system will decide which programs can use the CPU for a time slot. But sometimes, if for example, when you are listening to the music from the computer, it means you are running a program. Maybe it's a media player or something like that. When you are running a program which is used to play some music, and you just at the same time you just double click the icon of Word. Maybe it means you want to edit something while you are listening to the music. So at this time, after you double click the icon of the Word, it means you just launched an interrupt, because the mouse has to let the CPU know that the users want to do another want to do something else, except for the music playing. The user wants to do something else with another program, then the CPU has to respond to this interrupt launched by the mouse, and it will just check the number emitted from the mouse and decide to it just knows that the user wants to use another program called Word to do something. So it has to load the program and the a program from the hard or about the Word from the hard disk into the memory and build and generate a new process for this Word program, and to run some codes in the CPU to react to the request from the user. So basically, you can see the interrupt is very important for the modern operating systems. If there are no interrupts, we can't let the operating systems react to the request from the users in time. So this is the basic concept about the interrupt. We can have a quick look about the process to deal with the interrupt. So basically, we can divide it into 3 steps. It means first, if as we said, after the interrupt is sent to the CPU, it has to be prolonged. It has to be not it has. Okay, so when the interrupt happens, it might be dealt with immediately, or it might be put into the list and wait for the interrupt controller to push it into the CPU. And as long as the CPU decides to deal with this interrupt, we have 3 steps to deal with it. So the first step is to take the interrupt. It means in this step, because you have to use the CPU to deal with something about that interrupt. It means the last program running in the CPU has to get out of the CPU, because there is only one CPU in the computer. We just assume that only one CPU. That means this CPU, if this CPU wants to run some code for the interrupt, it has to let the last process or last program in CPU out. But when the last program gets out of the CPU, sometimes in the future, it has to return to the CPU to continue executing the subsequent codes, the subsequent instructions, the codes, right? So we have to record all the execution information about the last program. So the first step to handle an interrupt is very important for the last program in the CPU. We have to store the content of the program counter and PSW. If you can recall these 2 special registers, they have a lot of useful information in these 2 registers. And we have to store the information and push this information into the push the information onto the current stack of that last program, because each program has a stack to record some important execution information. So now the last program has to get out of the CPU. We have to record the current execution information. We just push them onto the current stack of that program, and then the CPU can contents of the register can be replaced by some other information about the next process. The next process will take the CPU to handle the interrupt. So we move on to the second step. So when the second step will just run some interrupt handler according to the interrupt vector. So what is this interrupt, so-called interrupt vector? Actually, sometimes it's just an integer because operating system has a list indicating which vector means which kind of events happens. So we just need to check that list and choose a certain interrupt handler according to the vector, according to the integer sent by the bus, because no matter it's interrupt from hardware or from the software, it will just send this. It will just send the relevant vector or interrupt to the CPU, and CPU will check the list to get the corresponding interrupt handler, and then it can run this handler. Actually, this interrupt handler is just a procedure or function which matches to the vector. And after the interrupt handler, it's basically is a segment of code, a segment of some instructions. After that, then we should we should return to the interrupted program. Usually, after we deal with an interrupt, we just return to the program, to the interrupt program. I mean, the last program before you deal with the interrupt. So that's the usual way. But there, it's possible that after we handle some interrupts, and we just maybe the CPU scheduler will decide to switch to another new program. But usually we just return to the interrupt program and continue to execute the next instruction of the interrupt program. I mean, from the last program before the interrupt handler uses the CPU. So these are the three basic steps for the interrupt processing. And with this interrupt processing, you can see anytime we want to do anything on the computer, you just need to send your request by click some icons or typing some commands. Then the operating system it will be aware of your new request, and some interrupts will happen, and the CPU will might deal with your interrupts immediately, or it might just disable your the interrupts, and after the CPU finish the important things it is handling, then it will just come back to handle your new interrupts. But you cannot, you basically you won't feel the delay about your request, about the response to your request, because it's very fast for the CPU to run the executions. It might just take CPU a few nanoseconds to finish its job, and then get back to handling your new request. So you don't need to worry about that. Why the CPU cannot just deal with my interrupt as soon as I send it. So this is about the interrupt. With interrupts, we can let the operating systems to coordinate multiple programs in the same computer, by sharing the same set of the hardware and software resources. So next part is buses. We just explain a lot about interrupt, and we will talk about it in chapter 2 or other chapters. It's very important, but now let's just move on to the next part about this buses. Bus is very important for the computer too, because all the components in the computer are connected over bus. They need to transfer data among the we need to transfer kinds of data among kinds of devices, among kinds of hardware in the computer, and we have to transfer the data over the bus. In the last figure, in the figure we showed you in the last class, it's just a very simple structure. But for now, nowadays, you can see the structure of a large x86 system is much more complicated. We have more than one bus to be responsible for the data transferring. For example, we have some special buses to CPU to connect to the memory. There are some buses for CPU to connect to the memory, and there is also bus for the CPU to connect to the graphics, to some special devices. We can even have a platform controller hub to connect a lot of devices. And you can see here some idle slots for some unaware devices. You can connect more devices to the computer based on this idle slot. So you can see it's very complicated for the modern computer with such complex buses, but it's all about it's more about the hardware, and on this course that's not our focus, so we just move on to the next part of this section, the last part. It's about how to boot the computer. About this process, when we as we said, when we turn on the computer, nothing is stored in the memory because it's a RAM. The memory cannot store anything if there is no power. But we have to run some code. When after the button is pressed, the first program or the first instruction or the code runs in the CPU is the how to say, is the BIOS. Okay, you can see its full name. BIOS is for the basic input-output system. It's the first software to run in CPU when powered on. So obviously, BIOS is not stored in the memory, in the RAM. So where is BIOS? Where is this special software? It's just usually when the manufacturer computer make the main board. The BIOS is fixed in some memory called ROM, and it's non-volatile. So it's just a firmware because it's some special software already fixed in the hardware. So after the power is on, we just need the CPU to fetch the first instruction from this firmware and to run some instructions from the BIOS and to do such things to get ready for the launching of the operating system. So basically, that's all about the computer hardware, and because this course is about the basic principles and methods in the operating system, about this spatial software. So our focus will be for the chapter 1. Our focus will be the first section and the fifth section. So we just need to learn some basic concepts, just view them as the common knowledge in this course or for our majors. They are just some common knowledge you need to learn, but you don't have to dig too much among these other sections. Our focus is the next important part is the fifth section. Before that, we need to take a quick look about the operating system rule. It means we have a lot of kinds of operating systems. There are kinds of operating systems which are used to different application scenario. And for this operating system, they have different evaluation criteria to evaluate their performance. For example, for the real-time operating system, the most important performance is the time you finish the job. But for the batch system in mainframe operating systems, maybe the most important thing is to just finish as more jobs or just run as much programs as you can. So the criteria are different for different operating systems. For us, we just need to know there are kinds of operating systems oriented to the different application scenarios. Actually, if you take a close look on this at this operating system, you will see maybe there are some overlap among the operating systems. But it doesn't matter. We just need to know that there are there are some different kinds of operating system. It's enough. So let's take a quick look about this part. So there are some mainframe operating systems which are used as high-end web servers. Usually, it has they have a great I/O capacity, which are different from our PCs. They even can have more than over 1,000 disks with millions of gigabytes of data, and you can see a lot of mainframe operating systems in data centers related to the cloud computing. So basically, this kind of operating systems they can be served for the big company or some business to business transactions. And even in the data centers. And you can see we have three different kinds of services can run related to this kind of operating systems, and they have different, as I said, it has different evaluation criteria. So this is the first kind, and the next kind is the server operating system. So sometimes if the terminals are limited at the at the computing ability, maybe it needs some servers to provide the terminals some services, and the operating systems running for these computers are called server operating systems. It can serve multiple users at once over a network, and allow the users to share hardware and software resources. For example, you can a few users can connect to one computer to share the printer connected to that to that computer, or if there is there is a server with large computing ability, the users can connect to this server and put their programs to this server and run at this server and get the results from the server. The users don't need to run the programs at their on their terminals. They just put the programs to the server and get the result back. So this is the second kind of operating systems, and you can see the typical server operating systems. We just listed them here, but I don't think you need to memorize these kinds of operating systems, because you just need to know there are some classifications, but you don't need to specify each one by memorizing the details. And next one is multiprocessor operating system. This kind of processors are used for those computers with multi-processors. And sometimes if you have only one processor with multi-cores, we can use this kind of operating systems too. Because for usually when we talk about the basic principles of operating systems, we just assume that there is only one CPU in the computer. We assume there is only one core without multiple cores, only one CPU in the computer. It means when we talk about the scheduling, the most important technology for the operating system, we think there is only one CPU. That means we just need to arrange multiple processes or programs on this unique CPU. But if there are more than one CPU, it just gets much more complicated, because you have to consider a lot of issues. If you just, even though you just need to run one process, which maybe consists of a lot of threads, you have to consider the consistency and some stability and some trackback, a lot of issues to consider. So you have to understand if the computer has multiple processors, the operating system, especially for the scheduling part, it will get much more complex. So this is this kind of this multiprocessor operating system. And also we have there are some personal computer operating systems, and I believe most of us are familiar with this kind of operating systems. And also we have some handheld operating systems, such as the systems running in on the smartphones. Android, iOS. Nowadays, maybe BlackBerry is already outdated. Most popular handheld operating systems are Android and iOS. So we won't talk the details in this kinds of various operating system, but you just need to know there are some classifications. Also, we have embedded operating system. So this is maybe in someone's opinion, it's not a typical operating system, because for this tool or even this including the smart cards operating system, there are no typical input and output devices. Maybe they don't need too much interactions between the machine and the users. Sometimes you might send your request to this kind of operating system, but it's very the requests you can send are very is very limited. You can, for example, if the embedded operating system is for the TV set, it means you can only press the button to tell the operating systems running on the TV set to change the channels or to adjust the color and anything like that. And for now, we have the smart cities, the smart home, just allowed us to send our requests in a more easier way, such as we don't need to tap something, we don't need to press some buttons, we just need to say something, because there are some modules to recognize our voice and to recognize that what we are gonna do according to our words, but not the text tapped into the machine. Anyway, it's just the different ways it's just a different input way. It doesn't change the essential operations for the operating systems, because basically no matter what kind of interaction no matter what kind of input ways, you just need the operating system to manage the resources on the machines, such as TV set, cars, microwave ovens. Even you can have the embedded operating system for a lamp, for a fan. So this is embedded operating system. You can see that they just need to focus on very specific behaviors of the machine. And of course, they have quite different evaluated criteria, right? And for the sensor node operating systems, they have relatively fixed input and output too, because each sensor node is designed for a specific event. For example, there are some sensor nodes to collecting the temperature information. There are some sensor nodes to collect the data information about the climates. Each sensor node, actually, you can view it as a real computer with smaller size. But it also has CPU, has CPU to run some codes, and has the memory to store the codes and the data, and it also needs to output something. But in most cases, they just output the data to the upper to another sensor node or to another computer with a large scale, and some people needs to handle those data from thousands or millions of sensor nodes. So the sensor nodes is basically used to collect the data, and besides except the sensor nodes, we need to set some computers to handle the collected data. And these are if you are interested in the sensor nodes, if you are interested in IoT, the Internet of Things, you might check more information on internet. But basically, the operating systems for spatial devices, machines such as TVCs and the sensor nodes, and even including the smart cards, the scale of the operating systems are relatively much smaller than the general operating systems, because they just need to focus on one or two on some specific behaviors, but they have their own criteria, they have their own rules, but it's not about the general basic principles or methods we are gonna discuss on this course. So we just need to know there are different kinds of operating system. Oh, you can see the last one we didn't talk yet is real-time operating systems. Because for these operating systems, they just focus on the time to get the response from the computer. It can be divided into hard real-time system and soft real-time system. You can check the details about these two kinds of real-time systems in the textbook. So I just ignore the details here, because it's not the focus of this course. For the classes today, we need to put more attention onto the fifth section, the basic operating system concepts. So you can see we just list a few concepts related to operating systems. They are most basic concepts for the operating systems, and you can even see that the concepts list here, they are just relate very closely to the chapter, to the content of each chapter. So you can see process this concept is related to chapter 2, and address space is about the memory. It's related to chapter 3, and this files is related to the software resource and related to chapter 4, and this is about chapter 5. For these two concepts, they are you can see that this one is about it's about the safe of the operating system. It means you need to protect some data from another program or another user. And also the share is about the interface program, the user interface program. So we just need to learn some important thing about these two concepts in this class, and then we're gonna explain much more details about these four concepts, because we're gonna learn a lot about how to manage the source software code files. We need to know how to, we need to learn how to manage the kinds of input and output devices, and also the memory the very important part of the computer. And if you want to manage memory, basically you are managing the address space for different processes in the memory. So it's all about the address spaces, and we need to learn how to manage the different processes. Actually, the second chapter, the title of the chapter 2 is processes and threads. We will focus on the first concept, processes. And processes, if we want to manage them, we just need to we need to store some basic information about the processes. And the most important thing is to schedule multiple processes to share the unique CPU in the system. So that's basically all we need to learn in the following classes. Before that, we need to understand the 4 basic concepts related to the following 4 chapters. So now let's move on to the first one, processes. So processes, as we said, they are highly related to the program. Actually, you can view a process as a program in execution. So you will see a program is a static concept. It's stored in the hard disk. And for the process, if you load the program from the disk into the memory, then it's not a static concept anymore. It's a dynamic concept. It has the cycle to emerge, to run, to execute, and to die, to disappear. So a process is a program in execution. When we say a process, it must have some it must be already stored in the memory. So in the memory, we have to allocate some maybe a segment or multiple separated segments to this process. Each process has its own address space, and this space it's just we need to measure this space, right? It can from 0 to some maximum, and this maximum means at most you can get maybe I say maybe 100 million bytes for process A and maybe 500 million bytes for process B. So each process will be allocated the part of the memory, because the memory, maybe the whole memory has the capacity about 8 gigabytes, and some maybe 1 or 2 gigabytes for the operating system, and the rest are the rest will be allocated to all the application programs in the computer, right? And each process, here you can see the process means a program in execution. So actually, if I say process, you have to understand this process is related to a specific program. So we say multiple application processes, they're gonna share the rest of the memory, and each one will get its own space. And this space, it has its own space, it has its own address. For now, I think maybe I shouldn't give you more details. If I give you more details about how to transfer the address, the process the address from the process into the address in the memory, about the allocation of the memory, about the address transformation. Maybe you'll get confused. So basically, you just need to understand each process in the memory has its own address space. It's a number. You can take it as a number, maybe 500 million bytes. And where is this 500 million bytes located in the memory? It's related to the another important issue, and we'll talk about this in the chapter 3. Okay, so you just need to know each process has its own address space, and sometimes this space is used to store the executable program. Actually, it's just compiled, and you get some you already get some instructions for this executable program. So the address space for each process will be used to store the executable program and the data to be processed by this executable program, and the stack to store the wrong information about this process, about this executable program. So that's what the address space for process is for. And sometimes you'll see we have only 8 or 16 gigabytes of memory, and we just allow allocate maybe 100 million bytes for a certain process. You'll see sometimes it's not enough for this process to run all the programs. So we'll talk later about how to use virtual memory to solve this issue. And before that, we just focus on more default information about the process. So we already know a process has its own address space in the memory. Besides, each process has a set of resources. It has the registers, open files, and related processes. We'll explain these related processes in the next slide. So you have to understand a process while during the execution of a process, it might open some files on the disk, and we have to record those information. Also, we need to record the information about the related processes. Also, a process is created by a certain user, right? As we just take the example. We take the word as an example. As we said, if you are listening to some music and you just record, you need to finish some report. So you should double click the mouse on the icon of word. So this user, you just click that icon to launch a program to be executed in the memory, and it means you are the user to create this process, and we have to identify the user to know which user created this process, and we use this user UID. We use this UID. Actually, it's just an integer number. We just use UID to identify which user created which process. So UID, you have to understand this term. It's just a simple term. And also, this user might belong to a certain group, right? You can for now the PCs, it has multiple you can create multiple users and group them into a different group. Each group has different permission to use the software, and so we need to identify the user of the user of owning the process belongs to this group or that group. So we use this term GID to represent this. And UID and GID is used for the file partition too. In the future, we'll talk about this, but for now, you just need to understand the meaning of UID and GID. Each UID can have a GID to represent which group that this user belongs to. So this is about some basic information of process. Also, you need to understand a process can create one or more other processes. And the created processes are called the child processes for this process. So in the first experiment, I require you to write some code, or you just need to maybe I have to give you the code, and you just need to understand the code and to observe the results and analyze it in the experiment. So the first experiment will have some assignments, will have some codes, some programs about the process creation. So you have to understand if a process created some child processes, and the child process itself is a process too, right? So it means this child process can create some child processes too. So you have a lot of descendants. And it may form a process tree like this. It means process A created B and C. So B and C are child processes of A, and B has 3 child too, right? B has 3 children too, D and E and F. So all of these processes, they are related processes, because they have this relationship between the father and the children, if we call them the father and children. A is the father of B and C, the parent of B and C. And all of these related processes, they need to communicate with one another. And sometimes they need to synchronize their activities. So it means they need to send signals or just send messages to each other. And these activities are called, these behaviors are called interprocess communication. And that would be the content of the second experiment. So for now, you need to understand it's very important to grasp the way to create a new process and to understand the relationship between the children and the grandchildren and even more. But for now, you just need to know the basic concepts of the process. It's just a program in execution. And in the chapter 2, we'll talk about how to how to schedule the most important hardware resource, i.e. CPU, how to schedule the unique CPU in the computer among multiple processes stored in memory during the same time. That's the basic content for chapter 2. Also, we'll discuss how to store this relevant information for each process. We have a spatial structure for each process, and you have to understand each process has different different statuses during the cycle, during its life cycle. Because we said when you double click the word, you just launched a process, and after you finish the editing job, you just close the word, right? And during the time between you open it and you close the word, close this software, it's the life cycle for this process related to the word. And during this life cycle, the process will switch from this data to the next data. There are 3 or 5 or even 7 statuses for a certain process. And those are basically all the content we need to learn in the chapter 2. And after that, this is about chapter 2, okay? And then let's move on to the next basic concept, which will be discussed in chapter 3. Memory management. In memory management, we just manage the address space for different processes. So the address, as we know, modern operating systems, they just allow multiple programs to be in memory at the same time. So, and each process has its own address space, right? The process A has its own 100 million bytes. Process B has its own 500 million bytes, right? And of course, you cannot allocate the same units of the memory to 2 or more processes, right? Each unit of the memory has to be allocated to only one process. They have its own, each process has its own address space, and all of these address spaces shouldn't be interfered with each other. They have its own, you just need to know this address spaces of the processes. They don't have any overlapping. And we also need to protect process A from process B, protect the address space from the from being randomly or being how to say, we need to process the address space for process A from being accessed by any other processes. Only process A has the right to access its own address space. It means process A cannot access the address space of process B, vice versa. And so we need to design some framework or the mechanism to finish this, to perform this job about the address space protection. Also, so this is the one of the important issues we're gonna discuss in chapter 3. Also, as I said before, maybe you just allocated, the operating system just allocated 100 million bytes to process A, but actually the process A needs more memory space, needs more address space to finish its job. for example, if you using Photoshop or some, maybe you just play a movie, a movie usually, if it may be over than 1 GB or even more, right? 2 GB is possible. So you cannot just, if you want to run a program to play a movie on your computer, and the data, I mean the data to be processed, the movie to be played, it needs over 2 GB to store. If you want to play this movie, you have to load the data of this movie into memory first, and then you can run some codes from the media player, from the player in CPU to decode those data and transform those 0, 1 series into the pictures and into the audio you can understand, right? You have to run the program on the data of the movie, and the data of the movie is over 2 GB. It means you might need over maybe 3 GB for this process. And as you know, the memory has only maybe 8 or 16, at most 16 GB. You cannot just allow let your computer run this unit program. Maybe you need to do something else. So maybe you cannot just allocate over 3 GB for one process. It's usually won't happen. So at this time, if the address space desired by a process cannot be satisfied, cannot be allocated at once. What do we do? What can we do to solve this issue? Because it's right. This process, during the life cycle, it will need over 3 GB to store all the data of the movie and to store all the instructions or the executed program. Over 3 GB needs to be stored in memory. So how to solve this issue? You cannot allocate it over 3 GB to a process at once. The basic way to solve this issue is to let this process to own a certain capacity of address space during different time periods. It means for in the beginning, you just need to play the first 1 or 5 minutes of this movie, right? So you don't have to load all the data of that movie into the computer, into the memory. You just need to load the first part. You just need to load the former part, the beginning part of that data of that movie, and you load the program into the memory, it's okay, and you just load a partial data of that movie into the memory. And after you already decoded all the data and just played it, you can just replace the next part of the movie into the same part of the memory, because you already played it out, right? You already played it in through the screen and speaker. So that part of the memory can be replaced by the first part of the data, the second part of the data, and until the end, the last part of the data for that movie. So maybe you just allocate maybe 100 million bytes for the data to store the data of the for that movie, but you just use it 10 times. It's just roughly speaking, it's a rough assumption. Okay, maybe it's not just 1, 2, 3, and 10. Maybe there are some exceptions, but basically the basic idea is to just keep part of the data of the movie in the memory, and then the next part, and then the next part until the final part. So if the data needs altogether, it needs 2 gigabytes, but you just allocate it 100 million bytes to store this data. You just need to replace them 20 times, and you can fix, you can solve the issue, right? And that's the basic idea of virtual memory, and this is very, very important for the memory management. We'll talk about this in chapter 3. And virtual memory, this idea can be how to say it can be used in a lot of scenarios, not only for the memory management. It's just an idea that you how to say, you get the space by but you get the space in a long time, but finally you can get a large space, right? So this virtual memory, you can see in the slides, we just say a process can has more address space than the main memory. How can this happen? Because we just use a long time to get. It takes a long time to get the process more address space. At first, we allocated you 100 million bytes, and after you used 100 million bytes to allocate to store the first part, then you can use it to store the second part. It means you just stored 2 million bytes in memory, just in different time. Just 1 minute ago, you have this part of 100 million bytes. The next minute, you have another 100 million bytes of data. So that's the basic way. And in this way, the operating system just keeps part of the address space in memory and part on disk, and shuttles pieces back and forth between them as needed. And during this process, we have to understand that sometimes we just in the last example about the movie playing, we just talk about the replacement of the data from of the movie, but actually sometimes the programs needs to be loaded into the memory one after another. Only part of the executed program can stay in the memory. So sometimes we need to change. We need to remove some data or program out and load some new program and data in. And how to finish this operation in more in a more effective way. It's the basic it's a basic technology we need to understand. In chapter 3, we'll learn some page replacement algorithms, and we'll see different algorithms. They have the different performance. So that's basically what we need to learn in the chapter 3 about the address space protection, and about the transformation of the address space. I didn't explain this in detail, but we'll see in chapter 3. And also we need to learn something about virtual memory, especially about the page replacement algorithms to help the processes stay in the memory in a more effective way. So that's about the chapter 3 about the how to management the memory. Actually, it's about how to manage about the address spaces. And next one is chapter the concepts, the most important essential concepts in chapter 4. It's about files. You must be very familiar with files because you all do a lot of things on computer and your smartphones, and the data they are just stored as files, right? You want to just take the movie playing as the example again. When you want to play this movie, you have to locate the movie, right? Maybe in your computer you have different directory. So you can see the directory is used to group files together. And files are they are just some stored data stored in some storage media, maybe in USB, maybe in your disk or hard disk or some SSD, whatever. Files just some data stored in the storage media, and all of these files they are gonna group together to form the directory. And as you can see, this figure is this figure is the directory tree for Unix-like or Linux-like systems. We have root directory, and then we have DV for the device, and the home for the users, for different users. They have a different directory. Home directory. This directory has two subdirectories, and user one have this subdirectory D1 and a specific file named F1. So this basically formed directory trees. And for now, we just come back to that example about movie playing. Okay, if you want to play a movie, you might have multiple directories in your computer. Maybe you have a directory for studying. Let's just call it study, and you have a directory named as entertainment, and you should open the entertainment directory, and maybe there are two or more subdirectories. One is for music, and the other is for movie. Let's just assume this, and then you need to. So first you need to open the directory of entertainment, and then you need to open the directory of movie, and then you have a lot of files representing a lot of different movies, and then you just double click that movies, right? That file. After you double click that file, you just launched, and the mouse will just give emit an interrupt to the CPU, and CPU will know, now the user just sends me a request. He wants to open this file named maybe 1.mpeg. Okay, so he wants to open this file, and I have to use a certain program to open this file, and because after you install some player, if you install some program to play the movies, it will build the link in the operating system. So it will know, the operating system will know which program to launch to play, to open this file, this movie file for you. And then the operating system needs to locate that program in the disk and load that program into the memory. And it also needs to locate the data, locate the movie file in the disk into the memory. So there is a problem. The problem is how to locate the movie file and the program in the disk, because the disk is very large. There are maybe over 200 gigabytes, right? And your movie files, it is 2 gigabytes. So where is this movie file located in the disk? That's an important issue for in the chapter 4. We need to understand how to locate a file in the disk. For now, you just need to know the operating system will follow the path name to locate that file. We need to, if you want to play a movie, you need to locate the program and the movie file in the disk and load them from the disk into the memory. First, you need to locate it. How to locate it? It's all based on the path name of the file. As we say, maybe let's assume that F1 is that movie file. Okay, so it means you have to create a path name, which let me just tab it, which just so for GUI, you just need to double click the icons of that F1. But if you are in a share, if you need to type your command to the operating system to let it understand your request, you have to use this path name. You have to create this path name named. First one is the slash for the root directory, and you just type home. It means you need to locate the directory of home to get the address of to get the subdirectory of U1, and you use slash as a separator for Linux or Unix-like systems. If you are in a Windows series operating system, you need to use the backslash. You need to use this backslash to act as a separator. So in Linux, this is a directory tree in Linux or Unix-like systems. So we just use slash. You just need to create this path name based on root directory and home and separator and slash as a separator, and you want this subdirectory and another slash for the separator, and then you type the file name of the movie file. So this is how to make it larger. Can you see it? Oh, okay. Anyway, I believe you can see it clear. The path name in red color. So you have to type this path name in the shell, and then the operating system will know that the file you want to open, you want to load, is located by this path name. And when they when the operating system analyze your typed path name, it will get a file descriptor. Actually, this file descriptor just a simple integer, and it will use this file descriptor to to locate, to get the store information, to get some information from the directory of U1 to get the specific address for F1. And then it will check the F1. There is a spatial structure called file FCB. Okay, we'll learn about this in chapter 4 in more details. Now you just need to know we have a spatial structure to store the detailed address of a file, and how to organize the address of a file. It's the main concept. It's the main content in chapter 4. So whatever, you just input the path name, and operating system will get the file descriptor and use this file descriptor to handle all the access, all the reading operations on that file, and load that file from disk into the memory, and then play it for you based on the program. So this is about path name, and I just typed you the absolute path name because there are two different ways to provide a path name for a certain file. The first one is called absolute path name. As you can see in the screen, it's red, and also you can use the relative path name. And what's a relative path name? Absolute path name starting the absolute path name starts from the root directory, right? And the relative path name, it starts from the working directory. You can see the working directory. What's the working directory? It means the current directory you are working at. Okay, so if you are in Windows, you double click a directory, you open a window for this directory. That's window that's in front, that's a foreground window. It just provide you the working directory. For example, you just double click entertainment, and then this directory is a working directory. If you just double click the subdirectory named as movie, then the movie is the working directory. So if you don't use the slash as a separator, you can just for this example, you can just simply type F1 because you are already in the directory of U1. U1 is the current working directory. In this case, you can just directly type F1 because the operating system is aware of the current working directory. If there is no absolute path name, it's just a search the file you just typed from the working directory. So for example, if now we suppose the working directory is U1, it means you are in this directory right now. And if you want to access this directory, you need to figure out how to create the path name, because these are some basic operations for the for this course. You have to understand how to switch between the absolute path name and relative path name. And in the quiz of this I already let you know that we'll have a quiz, right? The quiz will be held in the middle of the semester. It means you will have you'll have a couple of questions to answer in that quiz, including including some, how to say, you need to calculate, you need to explain something, you need to calculate some data, and you are might required to apply some algorithms to solve some certain cases in the quiz. And in the quiz, maybe we're gonna give you a question like this. I just give you a relative path name, and you need to change the relative path name based on the working directory into translate or transform this relative path name into the absolute path name. So you have to understand here how to switch between the two different path names. As we say, if the current working directory is U1 and you want to access this directory, so let's type it here. So the relative path name should be, you start from U1, okay? The relative path name should be double dots. Double dots means the parent directory of U1. So now you are in U1 in this directory. The current working directory is U1, and now you want to move to bin into this directory. So you have to type 2 dots to represent as you want to move to the parent directory of U1, i.e. home. So 2 dots means home. And then use a slash as a separator for Linux or Unix-like systems. And here the cursor just show us we are in home. The home is, and then we should use another 2 dots to represent the parent directory of home. And now we are in the root directory of this system, of this directory tree. And then we should type USR. It means we are in here, and then type bin. So that's the way we get this, hold on, we get to this new directory from the current working directory, which is U1. This is the relative path name. And for this directory bin, if we want to get its absolute path name, we should start from the root directory, use the slash to represent the root directory, and then USR. Okay, it is too ugly. So I just circled the relative path name for this case, and if we want to get the absolute path name for this directory, it's just showing as this circle, this squared. Okay, so this is the absolute path name, and the text in the circle is for the relative path name. So I just explain a lot about these two different path name, and I hope you all grasp this, because we may have a question about this in the quiz. Okay. And then let's move on to the next part of the files, the final part. So we just need to simply understand that in Unix like or Linux like systems, the devices, they are viewed as the spatial files. and they are all in this directory. And if it's a block device, it's just viewed as a block spatial file. And if it's character device, I will explain the definition of block devices and character devices in chapter 5. So you don't be worried. Just understand that the devices in Unix or Linux-like systems, we view the devices as some files. So when we want to input something from the input devices, it's just like all the operations are just like reading from some files. They are unique. And the last one is about pipe. You just need to understand the meaning of the pipe. It's just a sort of a pseudo file used to connect two processes, but it's not the emphasis of this course. You just understand this this term. You know what it is. It's enough. So next part is input and output management, devices management, which will be discussed in chapter 5. And in chapter 5, we're gonna learn first from the hardware perspective. We divide the device into two parts. Actually, we just talked about this in the last class. Also, we need to learn from the software perspective. We need to learn the 3 ways to perform or to finish an I/O operation. And also, we need to understand the 4 software layers related to I/O operation. Okay, that's basically the 2 main issues we need to solve in chapter 5. And then let's move on to the protection and shell. So we just explain a lot about the content we'll learn in chapter 2, in chapter 2, 3, 4, and 5, right? For now, it's just we just need to understand the protection is very important for the operating system technology too, because we for example, in memory, we need to protect the access. We need to protect the data of process A from being accessed by any other processes. And for the files in the file system, we should also protect if user 1 owned file A. If user 1 owned file A and user 1 just set some rules about the access to this file A, then the other users in the same system, in the same computer, they have to follow these rules to access the files. If they don't have the permission, they cannot access the file A. They cannot access. It means every user in the system has to access anything with permission. If there is no permission, the operating system will just deny your requests on the access to a certain file or a certain buffer or a certain unit in the memory. So that's called that's the one of the important issue related to protection. Of course, we have other protection issues, such as when you log in the computer, you cannot you cannot allow another user who doesn't know the password to get in your computer, right? So this is all about protection. But for us, we just need to focus on this file protection. Among those different protection issues, we just need to focus on file protection in Unix or Linux-like system. So we need to understand the 10 bits. Here it said 9 bits. Actually, a file has 10 bits to describe its basic information. The extra 1 bit is about the type of the file. We have 4 different files, and we'll talk about it in chapter 4. So for now, we can just focus on this 9-bit related 9-bit in the basic information of the file. This 9 bits just provide us the 3 different permission rules for different users. So the first, the left 3 bits. The first 3 bits are for the just provide us the permission for the owner, and the middle 3 bits are for other members of the owner's group. So here you can see the usage of UID and GID. As we say, each process will be created by a certain user, and that user has a UID to identify. And that user might belong to a certain group, and so each user will have a UID and a GID. Each user will have a UID and GID. So if a certain user wants to access a certain file, operating system will check these 9 bits of that file. And it will check if the user is the owner of the file, or if the user is in the same group with the owner, or if the user just is anybody other than those 2 types of users. So there are, you can see there are 3 different patterns, permission patterns for different users. The first one is for the owner. The second one is for the users in the same group with the owners. And the third one, the last 3 bits for the other users. And you can see the 3 bits, they just use R to represent the read axis, and W for write axis, X for execute. So this 9 bits, it just means for the owner, it can read and write and execute this file. And for the other users in the same group with the owner, it can read this file, execute this file, but it cannot write, cannot change this file. And for the other users, they can only execute it. They can only execute this file. So this simple way just provides a very high effective way to control the protection on the file. So that's about the protection. And for the shell, you just need to understand it's a command interpreter. If you recall the first figure we talked about in the first class, you will see there are 4. You'll recall 4 layers, right? Each application program wants to interact with operating system to ask for to send a request to the operating system. It has to use either a command or a GUI to send the request. So shell just is the first one. It lets the users to type command to the operating system. After the user types the command, the operating system can use the shell to interpret that command into a way that operating system can understand. Actually, it's just some system calls. We have different versions of shell. And also we have shell in Windows. It's just called DOS. If you type CMD at the left or the bottom, you can call that shell too. And for this shell, we'll talk about it later, especially when we need to discuss something related to the experiment. So for now, you just need to know shell is a command interrupt, and you need to type some commands into it. And when can you type the command? Only when the shell show a prompt, show some special character, and then you can type your command. Otherwise, if you type anything, the shell won't react to your command, react to your information. And so that's all about today. So after the 3 classes, I believe you just grasp the most important concepts in operating system. As we say, it's the basic the 2 important roles of an operating system, and the kernel mode, user mode, and the time multiplexing and space multiplexing. I mean, the 2 different ways to share the resources. Also, we just discuss a lot about the basic concepts of the operating system, such as processes, address space, and the file, the I/O input output devices, about the controller driver, etc. So that's all for today's class. And in the next week, we're gonna move on to chapter 2 to learn how to manage the CPU among multiple processes. Of course, before that, we need to finish the chapter 1 with these 2 sections. So that's all for today. Thank you. See you next week.